we were looking at in the previous lecture a medium or material that has some polarization density and therefore, a net dipole moment. And we looked at it physically and said that gives rise to surface charge as well as bulk charge. Exactly what these charges are, what do they produce, is what we want to see in this lecture. Finally, the effect that we want to see due to these charges is the field they produce or the potential they produce. So, our path of learning about what kind of charges they give rise to is going to be through these quantities only, because these are the quantities we are interested in. So, let us take some material which is polarized, right, and it carries polarization P. Then the potential we saw in the previous lecture at R due to this polarization is going to be given as 1 over 4 pi epsilon 0 P at R prime dot R minus R prime over R minus R prime cubed dV prime. dV prime means I am integrating over the volume over which this charge density is given. Now, to understand this, let me use a trick. If I take gradient with respect to the primed variable of R minus R prime, this you can easily show, and I leave this as an exercise for you, comes out to be R minus R prime divided by R minus R prime cubed. And therefore, I can replace this quantity here encircled by red by this quantity here and write V r as 1 over 4 pi epsilon 0 integration P r prime dot gradient with respect to primed variable 1 over r minus r prime dV prime. Now, let us do some manipulations. P r prime dot gradient of 1 over r minus r prime, I am going to write as divergence of P r prime divided by r minus r prime minus, this is divergence with respect to primed variable, primed divergence of P r prime divided by r minus r prime. All right, this is a vector identity. In 1D, it is very easy to see. In 3D, also is pretty easy to see, and you can just work it out. And therefore, I get the potential V r to be 1 over 4 pi epsilon 0 integration divergence with respect to primed variable P r prime divided by r minus r prime dV prime minus 1 over 4 pi epsilon 0 integration divergence with respect to primed variable of r prime divided by r minus r prime dV prime. Remember, we are looking at this polarized material. I can use divergence theorem for this first term and write this as 1 over 4 pi epsilon 0 integration 1 over r minus r prime P r prime dot n prime is this unit vector out of the volume, which is the direction of the surface element ds plus 1 over 4 pi epsilon 0 integration, I will take the minus sign inside, minus del prime dot P r prime divergence of the polarization density divided by r minus r prime dV prime. Let me write this in a slightly different form and you will see what these quantities mean. 4 pi epsilon 0 if there was a surface charge sigma on a similar volume, right, if there was a surface charge sigma and bulk charge rho and sigma, I will write the charge density as 1 over r minus r prime sigma r prime integrated over the surface plus 1 over 4 pi epsilon 0 integration rho r prime over r minus r prime dv prime or ds prime. What does this tell you? This tells you that as far as electrostatic properties, electrostatic potential or electric field are concerned, this charge density sigma is equivalent to this quantity and the bulk density rho is equivalent to this quantity here, the divergence of P. So, I am going to interpret in terms of as far as electricity or electrostatic properties are concerned, that given a bulk material with some charge polarization density P r, n dot P at the surface is like the surface charge density. And since these charges due to polarization are not free to move, I am going to call these bound charges. And similarly, the divergence of P r, I do not have to have prime here, is equivalent to a bulk charge density rho r. Again, these are not free charges, I am going to call these bound. You see, this is consistent with the physical picture we developed earlier, that the polarization gave rise to a surface charge as well as a bound charge, and you can see divergence is actually how P varies in space. If it varies, then it gives rise to a bound charge. If P was a constant, there will be no bound bulk charge, but there will still be surface charge. So, as far as electrostatic potential is concerned, P is equivalent to a bound charge surface as well as bulk, and therefore, the electric field will also be, which is the gradient of the potential, will also be equivalent to as if is being given rise to by these bound charges. Let us look at some examples. Suppose I have a cylinder of height h and radius r, such that r is much greater than h. So, it is like a very thin disk and it carries a polarization, constant polarization P. Then as far as electrostatic potential or field is concerned, this is going to be equivalent to a surface and a bound charge. Since P is a constant, there is no bound charge inside. However, on the upper side there is n coming out. So, P dot n will give me positive charge over the upper surface, with sigma being, since here P and n are in the same direction, sigma being equal to P dot n, which is P. And the lower surface will give me negative charge, because here n is in this direction and P is in this direction. So, it will give me negative charge minus sigma equals minus P. So, this, the thing shown in red out here, is equivalent to two large plates with plus and minus surface charges, and therefore, the electric field inside is going to be in the direction opposite of P, with magnitude being P over epsilon 0. That is example 1. Let us take example 2. Suppose instead I have a thin rod, again with P being given inside, with this length being much larger than this radius A here. Then I can consider this equivalent to, again since P is a constant, there is going to be no charge inside, no bulk charge inside, but the upper and lower ends again give me P as surface charge density, and since this is very small compare, the area on the sides is very small compared to the length, I can consider this to be equivalent to two charges p times pi a square separated by a distance pi a square L, and the field lines are going to look like this in this approximation. As a third example, let us take a sphere which carries a constant polarization. For a sphere, the n is same as unit vector r in spherical coordinates, n is same as unit vector r, and polarization p is p z. Then the surface charge sigma is going to be p dot n, which is p z dot r, and if you recall from the lecture on spherical coordinates, this is p cosine of theta. On this side, n is like this, lower side. So, what you see is that sigma is positive as far as cosine theta is positive. It goes smaller and smaller as you go towards cosine theta equals 0, becomes precisely 0 on the equator, and then becomes negative on the lower side, with a dependence p cosine theta. How about the bulk is bound? Bound rho, which is divergence of p, which is 0 because p is a constant. Now, this is equivalent to, if you recall, equivalent to a problem we solved earlier in which I had sigma equals sigma 0 cosine theta. And what did that give me? That gave me an E field in the opposite direction, whose magnitude was sigma 0 over 3 epsilon 0, and outside it becomes the field of two slightly separated charged spheres, positive and negative spheres, and it will become like a dipole field, which I did not do when I solved that example, but now you can see that the way we derived it, it was two oppositely charged spheres slightly shifted, which for outside the spheres becomes like a dipole. So, this will also give me precisely the same field. It will give me a constant E inside, which is equal to p over 3 epsilon 0, and outside it will give me a dipole field of a dipole p, dipole moment p, which is 4 pi by 3 r cubed p. So, what we have seen in this lecture is how I can think of the polarization as a charge distribution. Its divergence gives me the bulk charge distribution, bulk charge density, and its dot product with n, where n is the normal going out of the dielectric, gives me the surface charge density, and from that I can calculate potential and field.